Hi, I'm Mohammed, and this is my performance project. So, what I've decided to work on is a system where you basically have one of these cups. Let me remove this. You have one of these cups, and this is a static mesh. And when it hits the ground, it basically turns into a geometric collection and fractures into several pieces like this. Ploof. And so what I've decided to work on basically is a system where you basically have a spawner that just spawns a lot of these ones and breaks a lot of them at the same time. Uh, and so now we basically have a lot of stuff exploding and fracturing and whatnot. So before we begin, I'd like to talk about some hardware limitations or hardware considerations rather. And I think the most important thing is that this whole project is definitely CPU bound. So as I understand it, the CPU sends out commands to everything to do certain things, including the GPU. So if there's too much for the CPU to do, we're basically CPU bound, and if there's too much for the GPU to do, we're GPU bound. And just looking at the frame and game here, you can see that, well, we're definitely CPU bound. That's where the bulk of the work is. And I think that has to do with most of these physics calculations on top of the collisions, which is also calculations for the CPU to do. Um, but yeah, now another, I mean, of course, there are things for the GPU to render, but I mean, the bulk of the work is just going to be the CPU due to all of this, the spawning, the and the calculations. Now, as the memory grows, uh, it'll basically be more and more difficult for the CPU to, well, keep track of everything. The caches will basically overflow due to there being too many of these. So it'll have to check outside. So we'll have to check outside the caches and instead going to the RAM, um, which is 100 times slower. Uh, and well, yeah, we'll get cache misses due to how much stuff there is. Uh, and that's not that good because these static meshes and the geometric collections uh, and the actors are stored almost all over the place in the heap. Uh, the only saving grace is that the geometric collections themselves are structured arrays, which means that they are closer in the memory, which makes it faster to look up within themselves. But if we're looking for a certain geometric collection, it's still going to be slow, especially when we're spawning things so fast and destroying things so fast and switching things all over the place like this. But I'll show you now in my first iteration what I did to, well, sort of fix this a little bit at least. So what I did to uh, address one issue, which was that here's a chart, by the way. The first issue I wanted to address was just going from 10 pieces to 5 pieces instead. Since this means there's less stuff to render at one time, and there's also less calculations for physics and collision. On top of that, there's also less memory used, which just, I mean, it slows down the inevitable, which, I mean, you can see here that the FPS in the pre-optimization is at 10 and 15 at 1500, 1500 fractured GCs. But with 5 pieces for the geometric collections, there's still the instead 20 FPS for 1000 fractured GCs. Um, and it's just better. I mean, there's less. So I can show you. Switch to 5 shards. Bam, and now I mean, again, as I said, it's just stopping or not stopping, but delaying the inevitable, uh, and that is that the memory gets well filled up. Um, and I mean, it worked a little bit. Now there was another issue that I noticed, which is if you look at the physics tick here, you can see that as time passes by, this physics tick will continue to grow. And that's because that there's just more and more and more of these geometric collections which are fractured. which have to calculate collision and physics. So my next iteration then was to simply fix that. So what I did was that after about 7 seconds from these things getting fractured, I turn off the physics and collisions of them. So here's the function for when a geometric collection fractures. I basically set a time to 0. So here we start ticking and check, okay, are we over the time to disable physical after fracture? If we are, then we disable physics and collision. And so the way it works in the engine then is that we can actually change the time it takes before they disable. So if you check the physics tick now, uh, it will be a lot smaller. And that's because we're just not really calculating the physics and collision for that many things anymore. We're sort of stabilizing that. But regardless of that, the FPS still deteriorates. And that deterioration is due to, instead of having a lot of bigger chunks in memory now with the physics collision and whatnot, uh, instead we'll have a lot of smaller chunks that doesn't require a lot of calculations, but there will be a lot of them. Like over time, once we get to about 5,000 of these, it will have a lot less FPS. And so my next the next iteration basically is to fix that. So I basically stabilized the amount of fractured geometric collections we can have in this whole arena basically. You can see here in my third iteration that, or my in my second iteration, that at 5,000 we have 40 FPS. And so to fix that, I stabilized the amount of fractured ones we can have at one time with a pool. And then I also reuse already fractured geometric collections so we don't have to calculate the fracturing itself. So what I do is when we're about to fracture something now, I either do a fake fracture or a proper fracture. And a fake fracture is just switching the static mesh with an already fractured geometric collection. And I do this by checking if we can reuse fractured geometric collections from the mesh fracture handler. And the mesh fracture handler, which is a subsystem, holds an array of fractured geometric collections. So whenever a geometric collection is created, we store it in there. And eventually we'll not have to create new geometric collections and instead just use fractured ones. So I also created a data asset for this. So here, right now the pool size for reuse is 250. And another thing I do is that I spawn 250 of these cups and then they fracture. So I basically have a pre-fractured pool of 250 cups. So all of these, it's a bit of a chug in the beginning because we're breaking so many at the same time, but this can just be put over a load screen, you know. And so after that, we start using these when the rest of the when the spawner actually starts. So now, when these crash, they're not actually making their own geometric collections. They're using these. So they're basically teleporting these, putting up the physics and collision back on, and then having a 7-second delay again, and then stopping the physics. So with this, what I found is that, well, the pool is just stabilizing the memory. And it works really great. Now I can have this on for a long time, basically. However, there is still a problem. The FPS does deteriorate with time. And I do think, I mean, it's still better than before. Before at 6 minutes we had 38 FPS. Now at 7 minutes we have 47. But I think the deterioration is due to a memory leak of some kind. So future steps, I would like to fix that. And another thing is that I would also like to fix the static meshes to also pool like the geometric collections. Because right now, in essence, the smaller the pool is, the less I will have to keep in memory, and the less the cache has to consider at one time, which in turn means less risk of a cache miss. And on top of this, all geometric collections living in a single array is good for locality as well. So because we touch the same memory over and over again instead of looking at other parts of the memory, which takes extra time, and we just look past the cache and it takes 100 times more from what I've read, which is not good. But yeah, so what I've done with geometry collection, I'd like to do with the static meshes as well. And I'd also like to fix this performance going down over time. I think that's the biggest thing actually. But yeah, that's it for me. Thank you so much.